So, on your trig cheat sheet, do you have the following? Do you have that one? What do we call this? A trig identity. If you don't have this in your, we talked about how to get this, I think in almost every class. I guess we did not talk about it in here, but I want you to have this as a trig identity. And trig identities are ways to change up a trig function. So there's hundreds of trig identities out there. This is one. I want you to know that one. The other one I want you to know is that one. And the last one I want you to know came from what's called the angle sum function. I would have done something like this in class. We take a look at this one, and I said to replace the b with another a. This would have given you sine 2a equals 2 sine a cosine a, called the double angle formula. I want you to have all three of those trig identities on your trig cheat sheet, and we will add more to that in the future. All right. Beginning of the class, I want you to know a trig identity. We can use this trig identity. And it's important that we do, because I want you to see something. Today we're going to talk about type 2 and type 3 problems and the range equation. So a type 2 problem is one where we launch the object from the ground and it lands at a place that is the same height at which it was launched. So just can't remember. So let's make sure we remember how to do these. Let's go with 20 meters per second and 50 degrees. Why don't you guys take 2 minutes and see if you can tell me where it lands. And see if you are capable individuals. Let's go through it. I want to be as clear and as concise as possible. So let's start with setting up our little thing here. I think for these kind of problems, it would be best if you do my method for a while. And if you don't know what my method is, then follow along, write yourself some notes, and tell yourself my method. It's not complicated. It's what we've already done before. I just want you to lay out your information as clearly as possible. So I'm going to start with a vertical and horizontal side. The vertical side is the one that's going to have all of your motion variables in it. So delta y, vy initial, vy, a, and t. And the horizontal side experiences no acceleration, so it's just going to be delta x, or range. Vx, there's no acceleration, so Vx stays the same, and t. All right? Now, there are some things here that are pretty standard and happen all the time. But one of the things I want to encourage you to start doing is remind yourself that you have to choose direction. I'm going to choose those as my directions for positive. My launch was done at an angle. Let's focus on that for just a minute. Back.
Find the opposite. It's only finding like the little, like just a little bit of the line, not like. It's like
this will help.
Yeah.
The object's going to travel along this path, correct? Does that make sense?
Yeah.
The launch velocity at time 0 will be Vy naught. But Vy is going to change, right? Vx is how fast it's going sideways. Vx is not going to change. And for all of you who don't know this, me going through this is something that you should be writing down. I want you to understand this, and I will test for this. Vx is going to stay the same the whole time. I'm trying to draw arrows out of the same length, pointed in the same direction all the time. That's what I'm trying to do. Vy is being acted on by gravity, and gravity is acting this way. So after a few moments, the moment it leaves the ground, Vy naught is no longer that size. V is becoming Vy, which means it's some y in the future, I'm sorry, some velocity in the future, and it's going to be less. In fact, it's going to become very small, and at the very top, Vy will be 0. Vy represents velocities at some time in the future. Vy naught is the instant it leaves the ground. It's the only one that has the 0 next to it because it's the only one that represents a specific moment in time. Vy represents any moment in time in the future after time 0. So Vy is always changing, right? It's being acted on by gravity. All good there?
Thank you.
You're welcome. So coming back to this, I believe I have enough information to flesh this out. I need either 3 pieces of information here or 2 pieces here because we are trying to find the time. So let's go with the left side. Delta y is 0 for this style of problem because the object lands at the same height that it was launched. This is a simplification. It's a type of problem that is simplified because you can introduce a 0. Vy naught is going to be 20 sine 50, which we just got from the prior portion of the problem. A is going to be 10 meters per second squared. I chose upwards as positive, so this is positive and this is negative. At the same time, Vx is 20 cosine 50. It appears to me that I have 3 pieces of information. That means I have enough information to solve for the time on the left side. I can use that on the right side. So I'm going to use delta y equals 1/2 at squared plus Vy naught times t. 0 equals 1/2 times negative 10 t squared plus, this part, we can get a number for that, right? 20 times sine of 50. Make sure your calculators are in degrees. I know what I got. Hope you got the same. I got 15.3. That makes sense to me. It's less than 20. We all good? All right. Need to solve that for t. I'll factor out one of the t's, set it equal to 0, and that t makes sense. It was on the ground at time equals 0, but I don't really want that one. I want the other one. And as I've walked around, I've noticed some things. So factored out 1t. I hate doing algebra in front of you because I think it diminishes us both, but I'm going to do some algebra because I've been watching some mistakes be made. Algebra, I factored out 1t. I was left with this after I factored out the t, and then solved it and got 15.3 divided by 5. So this is 3.06 seconds. I know you guys are craning your necks. That's all I'm talking about right there. That all good? All right, that means the time was 3.06 seconds. 3.06 seconds. What's that? Go ahead. All right. So we're going to move forward, find the range. Now, the horizontal part, there's no acceleration, so range is always just Vx times t. So that's going to be 20 cosine 50, and that's a 12.9. And 3.06. I get 39.3 meters. just the angle part of the launch. So this is why we did some of the trig, was to kind of prepare us for this. I'm launching at 50 degrees and 20 meters per second. I'm going to need the horizontal component of the velocity, and I'm going to need the vertical component of the velocity. I walked the room and looked at what you guys are doing, and some of you guys are having trouble with this part. You have to create a triangle. So, and I'm doing this more thoroughly than I want, but I'm going to do it the whole way, because you should be able to do this by now. I'm going to create a triangle. This is a triangle I'm creating because I already have the angle. I'm going to label the opposite, adjacent, and hypotenuse. I'm going to write out the appropriate trig functions. Sine of 50 degrees equals opposite over hypotenuse, and cosine of 50 degrees equals adjacent over hypotenuse. I'm not going to worry about tangent, but the opposite is Vy naught, and the adjacent is Vx. I know I'm going quickly, but not terribly so. We've seen this before, and we've done trig. So it looks to me like Vy naught is 20 sine 50, and Vx is 20 cosine 50. Yep.
How do you decide, like, how do you know that the vertical is Vy naught and then the bottom is like Vx?
Well, I need to pick two components, and I can line them up with any coordinate system I would like. I am choosing to line them up with a coordinate system that corresponds to vertical and horizontal. Right? This is vertical. I'm sorry, this is horizontal, and this is vertical. I know that my launch velocity is at an angle, so I need the part of it that's going upwards, and I'm going to label that the y direction. And the part of it that's going sideways, I'm going to label it the x direction. But my actual velocity is in both directions at once. Right? This is my actual launch velocity.
Yeah.
It's at an angle. I need to know how much of it is sideways. That's horizontal. And I need to know how much of it is vertical.
Okay.
Does that make sense?
But why is it Vy naught and not just like Vy?
Because this is the launch velocity, the velocity at time 0. Vx isn't going to change because there's no acceleration sideways.
Mm-hmm.
This is how fast it's going upwards at the moment the object was launched.
Okay.
Every moment thereafter, gravity is pulling down on it and changing only this part of the velocity.
Okay. So we're marking it as the whole line, but is it just that little corner per se?
These are velocities. This is how
Yeah.
fast it's going. The object is still right here.
Yeah.
Yes.
Okay.
So,
I got it. Never mind. I got it.
okay.
Yeah.
I'm not sure I understand. Maybe if I didn't give you the angle or the starting velocity, you realize this would still be the basic triangle that would work for any launch, right? It's still going to be some starting velocity and some angle. This could be generic, right? I could take out all the specifics that are here. Get rid of everything that's specific to the problem we just did, and leave it in terms of something generic. Theta, this is going to be theta. That's going to be theta. This is going to be theta. In the bottom here, this is always going to be opposite over V naught. This is always going to be adjacent over V naught, which means that Vy naught will always be V naught sine theta. Always. For projectile problems, this is always true. And Vx is always going to be V naught cosine theta. That's always going to be true. If you don't want to learn trig, then you could memorize this. You'll have to memorize it because it's not on your equation sheet. And I don't want to see it on your trig sheets because I don't want you getting this confused with something else. But if you don't want to learn trig or you don't want to spend the time doing the trig, you could memorize that. Which brings me to an important point. And some of you are going to be able to follow this and some of you aren't. If you're able to follow this, by all means, please follow this. If you're not, I will tell you the things I want you to know about this, okay? Imagine a generic launch, just a generic launch, one in which the object's going to land at the same height that it was launched. So just like the one we just did. In this generic launch, I want to treat this symbolically. I don't want to put in any numbers. And I have a reason to show you this, and it has to do with your trig identities. So please follow along with this for just a minute. Vertical, horizontal. Delta y, vy naught, vy, a, and t. Range, which is delta x, vx, and t. We have information to put in here. First, delta y is 0. Now, I'm saying this from the very beginning. This is a special case of this problem, and the results we're going to produce only work in this case. If you use these results on other types of problems, they will always be wrong. I'm saying it bold and big right now. This is a special result that only happens here. Vy naught is v naught sine theta. That's a generic answer. And the acceleration is g. I'm going to set upwards to be positive and to the right to be positive. That'll make me have to put a negative sign here and a positive sign there. At the same time, the object has a horizontal velocity of v naught cosine. That is the generic value for the horizontal velocity. So I have all generic representation. I have no numbers. All right? We all good with that? Remember, we solve for the time on one side, plug it into the other. I'm going to do the exact same thing I just did, but without numbers. So 0 equals 1/2 times negative g t squared plus v naught sine theta. And I'm going to put this in parentheses just to keep it separate from the t. All right? I'm going to factor out one of the t's that I know equals 0, which is going to leave me with 1/2 times negative g t plus v naught sine theta equals 0. Still want to solve this for t. Now, I made the t a different color on purpose to highlight it. It's the variable. Everything else is a constant, right? This is a constant, and this is a constant. So these are things that aren't changing with respect to time. This will give me, let's see, v naught sine theta equals 1/2 g times t. So solve this for t, and I get 2 v naught sine theta divided by g. All right? I've just solved for t, and that's what I get. And this has no meaning outside of this problem, but this is how long the object is in the air. Again, based on delta y equals 0. Well, solve for t, plug into the other side. So oops. I put t in, put that expression in for t. And now let's solve for it. Range equals vx times t. So I'm going to put all that stuff in there. Range equals vx, which is v naught cosine theta, times t, which is 2 v naught sine theta over g. I want to smash all that stuff together and combine stuff that is the same. So I have a v naught and a v naught, so that's v naught squared times 2 sine theta cosine theta, all divided by g. Now, I put the 2 sine theta, cosine theta together for a reason, and anybody who paid attention at the beginning of the class knows the reason. So if you weren't paying attention, we can write this as V naught squared times the sine of 2 theta divided by g. This is known as the range equation. And it's in your textbook, it's online everywhere, so if you're online and you're trying to do your homework and you're looking up my problems, trying to see if you can find the answer somewhere, even though I gave you the answers, you'll come across the range equation. I wanted to show you where it comes from. It comes from our process of solving for time on one side and plugging it into the other. It's nothing special. But do you note that there's something very important and critical to understand, that this can only be used if delta y equals 0. So don't think it's a catch-all, that it can be used anywhere else. It cannot. Just because you find it on the internet doesn't mean that it has any other special use. It can only be used in this circumstance. You try to use it for a type 1 or a type 3 problem and it will not work. Right? It only works under this circumstance. But it gives us something to do that we could not do before. So no, because we put the negative in already when we did the equation.
Okay.
Does that make sense?
Yes.
So I don't have to make it negative there.
Okay.
It allows us to solve for the launch angle. And there's no other type of problem where we could do that. So I want you to try it. Let's go back to this problem. 20 meters per second. I want to hit a target that is 30 meters away. What angle should I use? The only way to do this, range equation. It's the only way. So the range equation says V naught squared times the sine of 2 theta divided by g. Really don't have much to do here. The range is 30. I'm launching at 20 meters per second, and I'm assuming I'm on the Earth, so g is 10. Pretty easy to use. So I'm going to put 30 equals 20 squared times the sine of 2 theta divided by 10. Now that's going to give me sine of 2 theta equals 3/4. Yeah?
Would that be -10?
Because if I did, I would make the 3/4 negative, and that would give me some weird answers.
Okay.
Now, be careful here. You have to take the inverse sine of 3/4, but then you have to divide it by 2, right? Because the sine of 2 theta equals 3/4. So I want to point something out here, and this part is important. So I do 3 divided by 4 and get 0.75. I do inverse sine, and I get that 2 theta equals 48.6 degrees. So I divide that by 2, and that tells me that theta equals basically 25 degrees. That all good? I don't know if you know this or not, but we're not interested in that angle. We're interested in half that angle, right? Suddenly, whatever angle would be over here moves into the first quadrant. There's 2 correct answers. Whenever you have to solve for the angle in a range problem, you're finding 2 answers. And that answer will be the complement of this one, whatever the complement is. In this case, 25 degrees and 65 degrees are both the correct answer. There's a low angle and there's a high angle. Look, it's football season. If the quarterback wants to get the ball there fast, they throw it the low angle. It gets it there sooner, right? If they want it to take more time, they throw it the high angle. It takes longer to get there. Same reason why when you punt, you generally don't punt a beeline pass at the low angle. You want to go over the defenders. So you punt at the high angle. You've known all your life that there are 2 angles for stuff like this, because every one of you has probably squirted a hose at one point or another, and you've squirted your friend in the face, and then you also rained it down on him, right? 2 angles to get to the same place. So there's always 2 angles, except for one, 45. Right? 45 degrees represents a special case. And I want to demonstrate this for just a minute. Repeat this problem for me, just for funsies, because like to see your face when things don't work. Oh, I erased that. I didn't mean to, but what if I want to hit a target further away? Let's say I want to hit a target that is 100 meters away. What angle should I use here? I know I've blown through our time for a quiz. I know the bell's going to ring in 2 minutes. You have to hurry. Why don't you try? Find the angle. Range equation again. I'll help you. 100 equals 20 squared sine 2 theta over 10. Every one of you reaching for your calculator, careful. I chose numbers that you shouldn't need calculators for. 100 equals 400 sine 2 theta over 10. Still trying to find our answer. 100 equals 40 sine 2 theta. 100 divided by 40 equals sine 2 theta. At this moment, you should all stop. You'll blame yourself or your calculator having calculator troubles, but what happens when you put this into your calculator? Right? Does it give you an answer? If it does, it's imaginary. What's the biggest sine can be? The biggest it can be is 1. Right? Right? Sine can only be between 0 and 1. Cosine can only be between 0 and 1. This means you can't hit the target. That's what this tells you, that there is no angle that will work. You didn't kick the ball hard enough. So don't always think it's the calculator or you made a math mistake. There are angles where you can't reach your target. All right. Have a nice day. We'll figure out the quiz thing later. So let me see if I can either jog your memory or teach you something fresh. We'll see which it is. The ball was launched at an angle of something, right? In this direction. This is the first quadrant, right? What's this quadrant? 2? This one? And this one? Sine is positive in which quadrants? Come on, unit circle people. Is it positive in the first quadrant? Is it positive in the second quadrant? If you don't know, try it on your calculator. An angle in the second quadrant is 110 degrees. What is the sine of 110? Your calculator knows whether to make these positive or negative. So what's the sine of 110? Is it a positive or a negative number? So sine is positive here. What's the sine of 290? That's in the third quadrant. I bet you get a negative number here. And the sine of 300? It's going to be negative, isn't it? So that tells me that the sine is positive here and here, right? Now, normally this wouldn't matter, but I want you to think about something. We got sine of 2 theta equals 49 degrees, correct? There's another correct answer that would give us the same sign that's positive. It's over here. I don't know what it is, but it's the supplement. It'd be 180 minus 48.9 degrees, whatever that happens to be. Normally, I wouldn't care, right? We're kicking the ball this way, so why would I care about this angle? I mean, if I'm throwing a ball over there, I don't normally worry about the one that I throw this way, do I? Right? Even though there's a possible positive angle,